All right, so first questions about any, well, let me turn your lights on. Anything we've covered so far? All right, go ahead. Anything? Questions? Really? Okay. I feel like we should do at least one of these problems that are magnetic. You got one for me? Any suggestions? Nothing? Huh? This is a, okay, never mind. Anybody got it? I mean, you got any problem you want to see? We did magnetic circuits, right? That's really nice to find inductance, right? You don't have a problem? Okay. How many did them? Let's try that. Nobody? Are you serious? A couple of people? If you haven't done it, you're in trouble. But I mean, I'm trying to just be honest with you. Do the homework. If you don't do the homework, don't expect to do well. As a matter of fact, I got a message from somebody asked, I'm doing too well. What are your suggestions? First and foremost, do the homework, review the stuff after class, as soon as you can before the next class. Keep up with it. Otherwise, you're probably going to have a problem. When you cram, you get a huge amount of information over a very short time, and you tend to forget it. In general, they've done tons of studies. I'm sure you can find them. But the biggest problem is that will not lead to long-term retention, and that's what you need for the final, because the final is comprehensive, includes everything, and it's closed book, closed notes. And I'm trying to just help you and encourage you. You got one for me, anybody? Nothing yet? Well, pick one. I mean, this stuff's pertinent to the quiz and stuff, so anyway. How about problem 461? Didn't I assign it? Right? All right, let's try that. So what do you have here? We really have something like this, right? Not drawn very well. This marker's about shot. I'm not going to hit you. One of these work. Wow. I'll just go and run that forward. Let me try to draw that again. So this is problem 461, and it's a good one. And I'll try to underscore the important things. So in this problem, they have a toroid. It really is made up, the cross section of this thing is made up, first it has, you're gonna have to help me out here. Do they give you the radius to the center, or what are the dimensions of this? Oh, of this, the big one? Say again?
Of the core. It says it 2 centimeter diameter.
I better look at this. All right, for this one, let's see here. 461, 2 centimeter toroidal core. Toroid has a 1 meter mean radius. Okay, so we got a 2 centimeter diameter toroidal core. Let me try to draw this the way he's talking about. He's saying right here, if we were to look at this thing, the diameter of this is equal to 2 centimeters, centimeters or millimeters? Centimeters. Now this thing's made of 2 different materials though. There's an inner material, and can you give me the radius of that?
1 centimeter.
Alright, so we have A equal 1 centimeter, and that means the outer radius B is equal to 2, or I should say half a centimeter, sorry. And this would be 1 centimeter. Let me just tell you what I'm saying here. Can you all see it in the back? This isn't drawn real big. You okay? All right. Here's what he's saying. This is not a homogeneous material. There's an inner core that has a given mu relative to an outer core. I'm going to draw this a little larger so you can all see. This is the cross section of this toroid. So it says here you've got and A is 1/2 centimeter, and then you have B, and B is 1 centimeter. So it's a sleeve, you might say. Now the inner material has some mu relative. What's the value here for mu relative 1, the inner one?
10,000.
So it's 10,000. And then the outer material has a mu relative of, what's that, 3,000? Okay, 3,000. I'm going to try this one. This is a great problem because it can be used to calculate inductance, everything, very easily. Y'all hear me on this one, class? Please watch this. Okay, now, if that's the case, and is this a diameter 1 meter or a radius? For the inner. Radius is 1 meter, so this radius here is 1 meter. Y'all with me? Now he's going to have a bunch of turns, correct, class? I don't know how many turns he has, but he has a bunch, right? N turns. What else does he have? Go ahead.
For 50 loops of wire.
So this is 50. Go ahead.
20 amps.
Okay, we got 20 amps. Go ahead. What else? What does he want?
The magnetic field density inside of each material.
He's after the B field then? All right. So what he wants is the B field inside each material. Now I'm going to go ahead and get the inductance too. And we can even talk about the total magnetic energy. Does everybody understand how the problem's composed? Everybody? It's just a donut, but there's an inner core and an outer core. Different materials. So if you look at this, if we draw the magnetic equivalent circuit, here we get plus to minus Ni. Call that the magnetic voltage, if you will. It's an MMF, magnetomotive force. Y'all with me on that, class? Now after that, when you think about this, we have 2 materials that are side by side. You all see that? How many see that looks like 2 reluctances in parallel? Just show of hands. Can you all see this or not? I'm just curious who can't. Because this should be obvious, right? All the material has an inner core and outer core. They are next to each other, right? So the way you would look at this, we'll calculate in a second, is 2 materials. They have the same voltage across them. This is like a voltage source. And from here all the way around to here, we have 2 materials that have parallel paths through them. They are in parallel. So you're going to have some reluctance R1, or yeah, I'll call it R1, and another reluctance R2. How many follow me on why I'm doing what I'm doing? Just to show of hands. Y'all with me in there? Does anybody not see why I'm doing this? I'm just showing you the lumped element model with something that's very familiar to resistances and voltage sources, right? But that's a reluctance, and that's an actual MMF, or N times I. So next we have to calculate them. Now, suppose, and let me do it here. If we're just talking about the inner core, right? Right there. If you take a look at this, magnetic reluctance, first, is a constant cross-section for the inner core, class? How many see it is, right? Constant cross section. That means we can say that the reluctance for that one, and I'll put it Rm1, or just R1, it is a reluctance, right? R1 is going to be proportional to the length, inversely proportional mu, and inversely proportional to the cross-sectional area. Does everybody follow? It's just like the resistance calculation, except instead of sigma, you put mu there. How many see this? You good with that, class? Can you all see this in the back? I mean, all right, I've got to make sure at least you can see it. All right, so this, now, if you think about this, for reluctance, what is the total length around that inner, or the core? Class? You'll see it's just going to be 2 pi times the radius, 1 meter. How many see that? That's the total, same way the toroid. So it's 2 pi, right? 2 pi times 1. You don't need that there. That would be in meters. Now, mu, I'll just put mu1 here. Mu relative 1 times mu naught. We can substitute in the 10,000 later. Y'all with me, class? What's the cross-sectional area of the inner core? Class? Pi a squared. Are you all with me? Everybody? So that comes out to be what? So this is going to be pi, and I'll just put a squared. I don't even have to put the value down. It is a half centimeter. Y'all with me? We'll do that at the end. I'm going to see this right here. In the far back, are you guys, can you see this okay? Okay. So that would be the reluctance of the first one. Now, what's the reluctance of the second one? The outer part, right? And I'll just draw it here. So if we take a look at the reluctance of the outer part, this would be the cross-sectional area. Here is B, and here is A, right? Y'all with me, class? Can you all see this? In the far back? All right, so what's that reluctance going to be? I'll put it here. Reluctance 2 would be, it's proportional to the length, same length. Y'all see that? It's the entire length around there, which is 2 pi, right? Then it's divided by mu relative 2 mu naught. Now, what's the cross-sectional area here that I'm showing you that's shaded here? Class? How do you get that? It's cross-sectional area, right? If it was just a radius b, it would be pi b squared, wouldn't it? Now, if we subtracted the area from the inner part, that would give us the area, right? You all follow me? So it would be pi b squared minus pi a squared. How many see this? Okay, I'll put that down. So this is really going to be pi. It's b squared minus a squared. Now I put this stuff, we can cancel that pi business and stuff, but you all see I put it in terms of 2 resistance. We're going to get the value in a second. Everybody with me? How many see this right? All right. Now, the next thing is, I'm going to try to simplify. I'm going to get rid of the pi in both, and I think everybody can see this is not a major change. You all with me? Now next, after that, I'll do this here. Now I want to see what the parallel combination is of R1 in parallel with R2, the reluctances. You can do it either way. You can take R1 times R2 over R1 plus R2, or you can take 1 over R1 plus 1 over R2. You understand me, class? So I'll do it the latter, and I'll say it's 1 over R1, there's R1, so it's going to be 1 over mu relative 1, mu naught here. Let me erase this. And then it's going to be a squared, right? And then it's over 2. And it's plus mu relative 2, mu naught, and this is going to be what? B squared minus there, a squared, right? Over 2. And that would be the value. Does everybody follow me on this? Give me a show of hands if you do. Y'all with me? I just took 1 over R1 plus 1 over R2. They're in parallel. If you want to, I mean, you can multiply top and bottom by 2. You can see how this can be simplified. If I do that, put a 2 here, right? Then you can factor out mu naught. Do you all see that, class? And you can say that that parallel combination, I'll just say R1, 2 would be equal to 2 over, and then you can take mu naught here, and then you have mu relative 1 a squared plus mu relative 2, and then erase this. Mu relative 2, and here you're going to have b squared minus a squared, and that's going to be the value. Is everybody with me in this class? Now, what's my next step, anybody? I've just calculated the equivalent of these two, so effectively what I've done is take this circuit and reduce its complexity to this. This is going to be Ni, and I've got a single resistance here, or reluctance, R12, and there it is. What's my next step, anyone? Anyone at all? Come on, you guys know this. If you had a voltage and you had a resistance, what might be the next thing you calculate? The current. What is current really in the magnetic equivalent? Flux. Do y'all follow me there? How many understand that? So the magnetic flux flowing here, this would be the total magnetic flux. That would simply be Ni over the reluctance. And that would be the total magnetic flux, whatever it is. Do y'all follow me on that, class? Yeah.
In your previous lecture on Friday, you equated that y to.
Equated what?
Equated that y
That's not Y, that's psi.
psi.
It's the magnetic flux. Yeah.
Yeah. Psi to I.
It is.
Or L or Ln.
Whoa. I, the current, in this case, is like the magnetic flux. Ni, the actual value of current times number of turns, is like a magnetic voltage. It's just the MMF. You all with me, class? And therefore, the reluctance, which is like resistance, is there. So if you want the magnetic flux, like I for an electric circuit, for a magnetic circuit, you simply take Ni divided by the magnetic reluctance, and you have a flux. How many understand it? This is a simple concept. It's just follow. All right, if I've got that, now we can calculate this. You agree? How many did this problem? Anybody? Didn't I assign it? Nobody did it? Really? Oh my gosh. I gave you a gift. If you didn't do that homework, oh gosh, you hurt yourself. All right, so anyway, this would be the magnetic flux, right? Now, we want the B field in both sides, right? We're going to have to calculate the B field in both materials. Do you all follow me on this, class? So how do we do it? By the way, at this point, if we have magnetic flux, can anybody do this calculation for me? Here's the reluctance. Can you give me this value? Just I'm curious. Can you give me that value real quick? If you don't mind? Is there something going on I'm not aware of? Are you into it? I mean, the quiz is going to use this stuff too in the person. Anything? Nothing? I mean, we won the game. I was happy about that. We crushed the entire weekend in 5 minutes. What's that? I couldn't hear you. What?
Oh, I just had an
How many had an exam today? My sympathies. I'm sorry. That was a heck of a win, but it's better you take it after a Sunday than after a Thursday, in my opinion, based on everything I've seen. I don't care what people say. Friday exams always have the average lowest scores. And Monday, highest ever, even if it's the Iron Bowl. All right, so can somebody give me that? Anybody? Just give it a shot. I'm trying to help you. Analog, huh? Who's teaching analog? Foster? He's a really good guy. You got a great guy. How many did okay? 1, 1.5, 2, 2.5. Whenever I see this, I say, oh. Oh gosh, I got stories about students. All right, anybody? 4 pi times 10 to the minus 7. This is one you should really know. 4 pi times 10 to the minus 7. It would be henries per meter. Please know that. If you're electrical engineers and don't know U naught and epsilon, you're going to look at you like, you're really an electrical. You sure you're not making the journalist?
I
Huh?
don't know if the value I got was right, but I got 0.000889. But I also didn't convert the centimeters to meters.
What?
I didn't convert.
That's important.
Yeah, so that's kind of fun.
That's real important. Because you're going to see something. When you convert centimeters, right, when you put 10 to the minus 2 here and you square, you get 10 to the minus 4. And you notice how those mu's are times 10 to the 4th or 10 to the 3rd? So it's going to reduce the size of that significantly. Y'all with me, class? Just give me the back. You got it? Well,
Yeah, I had 494, but I also forgot to do the centimeters. So I think it's.
this is one of the really low points in participation and accuracy. Anybody? Jonathan, you got it for me or not? All right, we're just going to go with the fact when that comes up, we can talk about it. Y'all with me, class? Now, that's light current, right? Hear me. Anybody, if you knew this, the total flux, which is light current, total flux, how would you get the flux through one of these? I'll call it, how do you get it? Anybody? It's a question. Current division, right? Flux division. Same deal. Y'all follow me? Here's the parallel. Here's the similarities. Let me erase that while we talk about it. So come over here. All right. So next, how do we get the flux through 1 and then the flux through 2? Well, first we should have the total flux right here, right? But we're still waiting for that value. Anybody have the reluctance of the two in parallel or not? 335? All right. All right, I'm just going to say 335, okay? It's magnetic reluctance, whatever the units may be. Now, to get the flux here, what do we do? Well, you take the total flux, right? Just like current. You say current division, you're exactly right. That's the total magnetic current, right? Now, what do we do? If we want the one through the first one, we take the opposite reluctance, right? Over the sum of R2 plus R1. Y'all agree with that? How many do? Right? What's that going to be? Well, whatever the total flux is, I'm going to assume you're right. Oh, sorry, that's the resistance. Total flux, or reluctance, I mean. So we take 335. Give me this one too. I'm assuming this is right times Ni. Well, was it 20 amps and 50 turns? All right, so it's going to be 20 times 50, right? And you can give me that value in a second. That's that total value. But then when we do this, what do we get? We get the total flux, whatever it is, and then we multiply it by the reluctance of 2, which is there, over the sum of the two. So it's going to be 2 over mu relative to mu naught, and it's going to be b squared plus a squared. You probably would have these stored in the computer, over the sum of the two, which is that, plus 2 over mu relative 1 mu naught, and this would be simply a squared. Let me erase all this too. And then you can see, I'm just putting this up here, I'm putting in the values. Y'all follow me in this? I'm simply taking the values for the reluctance of the first, reluctance of the second, putting them into this equation. You'll see obviously a lot of cancellation. We can get rid of mu 0, right? We can get rid of the 2 for starters, right? At this point, it doesn't matter how you do it after this point, because you can multiply everything by 1 over b squared plus a squared if you want, and then multiply by mu relative 2, so you would have one term left at the end over here. But can somebody just tell me, tell you what, let's start here. What is this value? 200 or 20 times 50, right? That's really 1,000 over 335. What do you get?
2.82.
And that would be Tesla, or I mean Weber's, pardon me, Weber's, not that. This would be Weber's if we did it right. All right, now, can you give me that? Just do the ratio. Oh boy. I'm sure there's a quicker way to do this, but I can multiply top and bottom by mu relative to b squared plus a squared, and you're left with 1 over 1 plus, and then it's going to be wait a second. That should be divided by. Oh, I messed this up. This should be divided by that. That should have been written that way, my bad. And then if you multiply that, you get that plus mu relative 2 times b squared plus a squared over mu relative 1 a squared. And out of curiosity, what is this going to be? I got to multiply it by psi t. Anybody? Y'all follow me what I'm trying to do? Just tell me what that is anyway. So we got 3,000 over 10,000. That's 1/3. Oh boy. Anybody?
15.
What? 15?
Correct.
Stop. 15? Wait a second. 1 over all that stuff's 15? It's got to be less than that. It's current division, not multiplication. Right? If you just did this, it'd be 1 over that. Does everybody follow me what I'm trying to do? You don't see it?
0.06.
Anybody not see it? Only thing I'm trying to do is use the concept of current division to apply it to flex division and find flux. What do you think that again?
0.0625 P.
0. Say it again.
0.0625 times psi.
625 times what? Oh, times. All right, that's okay. Just leave it like that. Psi total. Now, how would you get the current here? I mean, the flux here. Well, you know the total flux, right? That's the flux going through the other circuit. Just subtract it. So this is going to be what? It's going to be total flux, and it would be 1 minus that 0.625 would be the flux through 2. I don't really know what that is, but you all follow me? Now, after that, they want the B field, right? Let's finish this. How do you get the B field? You got the flux, it's Weber's. What are the units of the B field, class? Weber's per meter squared. So what do we do with this to get B field? We get a region. Divide by the area that it's going through. It's just like current density. Y'all follow me? All right. So how do I get? Let me try it here. I don't know if these values are right, but I'm trusting you with that. So if I wanted to get the B field in 1, it would be the magnetic flux flowing through 1 divided by the cross-sectional area of 1, right? That's simply going to be that magnetic flux 1, which is whatever. What is this value? Point what?
0.37.
All right. So it's just going to be whatever that is times 0.375, right? And then it's divided by the area, pi a squared. Y'all agree with that? How many see it? That would be the B field. Yes, sir.
Well, it would be the flux of 1, right? Not the flux of 2.
Oh, I'm sorry, 1. You're right. It's my bad. 0.65 or 625. My bad. Thank you very much. 0.625, right? I don't know what that is, but you all follow me how you can do this methodically, right? What about the flux in the second one? Anybody? I mean, not flux, the B field in the second. Take flux flowing through the second one, right? Sorry. Over A2. So that's flux in the second one, right there. Divided by area 2, which is pi b squared minus a squared. Normally when I do these things, this is me personally, on MathCAD, I have all the values calculated. I mean, they're up there, and I just, have a symbol for them, but I do the calculations right off the bat. Then I plug them in as needed, and they're available, and I get the final result. But there's nothing, if there's any, like if I mistype something wrong, I just change it and automatically changes it everywhere. MathCAD is very nice for that. All right, so that would be B2. Do you all agree with this? Now that's what he asked for. But if I wanted the inductance, pay attention to this. If I wanted the inductance, what would I do? Anyone, everyone. Hopefully you know. Well, what is inductance? It's total flux, right? Now, here's where you need to be careful. Remember, right there are n terms. You all hear me, class? There wasn't one term that caused it, there are n terms, right? So you find the flux flowing through one term, and that's simply the total flux we calculated. Then you multiply that by n. That's called the flux length per turn. How many have heard that concept before? If you took power, you should have. So now you multiply that times n, and then you divide it by, anyone? The current, right? Divide it by the current causing the flux. And then you get the inductance. And that's it in a nutshell. I mean, really, there's nothing more I need to say about that. That's the concept. This is the way you do it. You have anything with a whole lot of terms, and the flux is contained. Find the total flux flowing by finding the magnetic reluctance. You don't have to do it this way, but it's easier. The magnetic reluctance. And then multiply by the number of terms. That's the flux length divided by the current. You got the inductance. It's not even a trick. One thing I'm going to mention about this, and let me do it over here to show you something. Now, you're going to find out in some books, I mean, they'll have everything in terms of integrals and everything like that. They will not make it that simple. But it really is not that hard. That's about as simple as I made it. But here's something to keep in mind. And I want to show you guys something, because we're going to get into transformers too. If you have something, let's just say we have a toroid as such, and we have a value, make it radius A here, and we have a cross-sectional area A. Doesn't matter. It doesn't matter if that cross-sectional area is circular, rectangular, it doesn't matter. You understand me? It really doesn't matter when we're talking about magnetic flux. We're going to assume that this thing, we're trying to show you this is cross-sectional area A here. I'll make it square. So this is the cross-sectional area here. And if you have mu relative here as the permeability, we're assuming that mu relative is, of course, much greater than 1. And then I do this. I put N1 turns here, and I put N2 turns here. Now, this is something we call a transformer, right? You got turns or a magnetically coupled circuit. Turns on the primary, turns on the secondary. And I want to know the mutual inductance between these. How many have heard the term mutual inductance? I've covered it once already. It's what? The flux caused by the first set of coils linked to the second. Y'all hear me? So when we do this, the step would be simple. We calculate the total magnetic flux created by this set. You can put a current I in. So that total magnetic flux would be N, this is total, N1, it would be times I1. That's the magnetic voltage over the magnetic reluctance, and I'll just call it magnetic reluctance, and the total magnetic reluctance here is the length around here, which would be 2 pi A, divided by mu relative, mu naught, divided by the cross-sectional area. That's the magnetic reluctance as we go there. Y'all follow me? You've got that. You check that box. After that, now you have the flux, right? Now you find the amount of flux linked to the second set of coils. Each turn links one, you might say flux unit of 1 times the actual magnetic flux, but there's N2 of them. So that means the flux length through the second coil is going to be that, where it's N1, I1 over the magnetic reluctance, and then it's going to be times N2. Now I have the total flux linking the second set of coils. Then I divide that by the current causing it, and lo and behold, now I have the mutual inductance. Sometimes it's labeled this. It doesn't matter the symbol. Follow me on this, class? I'm trying to show you the simple thing. Y'all understand? All right. Now, yeah. Pardon me? The flux linking the second set. It's N times the flux through one set of coils divided by the current causing. Remember, inductance can never be a function of current for any linear system. You understand that, class? It's only a function of geometry and the material values, like the permeability. All right. And with that, yeah.
What would make it a nonlinear system?
Nonlinear materials, if you have a mu relative, it's a function of the magnetic field intensity. We'll talk about that next time. All right. Could you spread out? Yeah. I mean, at least one seat, preferably more than one between you and your neighbor.